So any other questions in the mixture model as a model itself? So can somebody respond? Is it making sense or this is going beyond? If so, where I can repeat anything if you want, or is it very simple, move ahead, I'll move ahead.
Yeah,
Sir,
actually,
go ahead. Sorry.
no. I was about to say, I mean, I was clear with this part.
Okay. So the other, Sophia?
Yeah, I was just going to say that my earlier question about how do you figure out if the model is good or not, that was more about that RHS part, that whether that is representing
That,
it
see
or not.
that, yeah, so that there is a identifiability problem, as I said, yes.
Okay, got it now.
Hmm? Okay, so both doubts are cleared, so let's go ahead with estimation, right? So suppose I have data and I want to do MLE estimate, then how do I go about doing it? MLE with mixture model. Okay. Now, if I have to do MLE with mixture model, how will my function, the optimization problem look like? Okay, first of all, let me write the mixture model again very clearly. So let's assume the components are each coming from a exponential family model. That means this is equal to some Wi transpose phi I of x by zwi and I equal to 1 to c. So maybe 1 to k. So maybe the first component belongs to is a Gaussian distribution for 1 phi. Second component is a maybe exponential distribution. Third is maybe some other gamma distribution, so on and so forth, right? But typically in a mixture model, to simplify things, let me assume that all the components belong to the same model. Not only they belong to exponential family, they belong to same model. That means what? The phi sufficient statistics are same. Let me make that assumption just to make the formulas simple. Otherwise, the formulas will become more complicated. So what is the difference in the components? The form of the distribution is same. Only difference is the parameters. The parameters are different. That means maybe all are Gaussians, but which Gaussian is different in each component. Okay. So is this part clear? How am I choosing components? Component models?
Yes, sir.
So all same model from exponential family. That's how I'm choosing. That's generic enough. Next, what are the other variables? The other variables are alphas. What are the constraints on alphas? They should all be greater than or equal to 0 and they should add up to 1. A simple way of writing these constraints is I'll say alpha belongs to delta k. If I say alpha belongs to delta k, it means there are k alphas and each of them is greater than or equal to 0 and they sum up to 1. Okay. Okay, so the name for delta is simplex. It's called k-dimensional simplex. Anyway, now what are your parameters overall in the mixture model? So the mixture model actually is a mix of these components using the mixing coefficients alpha I, pi of x, which is equal to I equal to 1 to k alpha I e to the power of wi transpose phi of x by zwi. So what are the parameters for the mixture model? Can anybody help me? What are all the parameters for the mixture model P? What are all the parameters?
Alpha
and
is
W.
1.
Alphas, all alphas, very good. And then
W's.
all W's. That's all, right? This is just to make sure you are on the same page. Okay. Okay. Now, what is MLE? MLE basically says maximize with respect to thetas, and if there are any constraints on thetas, put them, and then I equal to 1 to m log t theta xi. Correct? Now I'll just substitute this formula for p theta. What will I get? I'll get max over theta. But what are thetas? Alpha belongs to delta and w1 to wk. These are my parameters. And then with respect to each sample, log, and my likelihood itself is a summation, j equal to 1 to k alpha j pj xi, right? And what is pj xi? Pj xi is simply e to the power of wi transpose phi of x, so wj transpose phi xi by zwj, right? Okay. So everybody is convinced that this is the optimization problem I have to solve? Yes, no?
Yes, sir.
So, okay. So, this problem happens to be a terribly difficult problem to solve in general. It's a non-convex problem, that's fine, but it's intractable most of the time. I mean, in a general case, it leads to an intractable optimization problem. Okay, and what exact intractability is there? All that the papers I have already cited in the summary notes. Those are details not very relevant for us. It is for theory, CS theory guys. Anyway, I have already cited them. But there are some ways to solve it anyway. So the hope is that you will reach a stationary point. So if you have a general function which is non-convex, something like this, you will be happy if you reach a stationary point. What's the stationary point? A point where gradient is 0, right? So there are many algorithms using which you can reach such stationary points. And one of them is what is called gradient descent, and the other one is called as stochastic gradient descent. Hopefully, if we get time in this course, we will spend time on gradient descent and stochastic gradient descent later. So for the time being, since we'll anyway cover them later on, I'll give details of some other algorithm which is called as expectation maximization algorithm. Okay, maximization algorithm. Okay, it's called EM in short. Okay, so what is an EM? What is EM algorithm? It is an alternative to gradient descent, something like gradient descent. Why am I talking about gradient descent? Perhaps most of you know intuitively what is gradient descent, so I'm comparing with that. So it is something like gradient descent, which will give you a guarantee to reach a stationary point for this particular yellow highlighted optimization problem, which is in general intractable to solve it optimally. Okay, now the details of the derivation of the EM algorithm I have already given in your summary notes, but for your batch it is not important to understand the details of the derivation. What is important to understand is how is it intuitive and why does it make sense. Okay, now EM algorithm is an iterative algorithm. You start with some initialization for the parameters, initialized theta, so theta 0. So that means what? You have values for alpha and you will have values for each of your w's at the 0th, at the start, right? And at the ith, at the jth iteration, or j, I, k, all of them are used, right? So at the pth iteration, you do the following update, and you do these updates at every iteration. Okay, now every iteration has two steps. One is called the E step, okay, where you estimate, I'll write the formula and then try to explain. You'll estimate the posterior of the cluster ID given the examples with the p minus 1th iterate of the parameters, right? So if you are in first iteration, you already know theta 0, right? So with that theta 0 value, you can always compute what is py given x. How will you compute? Again, as I've told, this is with the old parameters p of y into p p minus 1 p of x given y. But what is this same as? This is same as alpha p minus 1 of y, and then this is same as e to the power of w p minus 1 transpose y phi of x. As simple as that. This is the formula, right? Okay. So what do you do in each step? You simply, with the current values of parameters, you infer the likelihood, the likelihood of each cluster ID given the example. Okay. Fine. And then what do you do? This is called the E step. And then you do what is called as M step. In M step, what you do is you simply apply the following updates. See, this is trying to get an inference for the cluster ID, right? What M step will do is it will try to update the values of the parameters, okay, in the following way. Alpha p of y will simply be sigma over I equal to 1 to m p. Oh, p is already, I used p for iteration, but p is already likelihood, so that's a bad notation. I should have put q everywhere. So this is q. So this is q. We are in the qth iteration. So then I'll take p, theta q minus 1, that is the current posterior, with xi, and then see, let me tell you what will be the usual formula if you have, okay, let me not confuse you. This is simply this by this. This is the proportionality. Okay, let me write proportionality. Okay. Okay, this is confusion, proportionality. Okay, let me write again equality. This is j equal to 1 to k, sigma equal to 1 to m, p theta q minus 1. Let me write the formula, then I'll tell you why it is intuitive. J given xi. Now, there is also a similar update formula for W. I'll shortly write it. But let us see why this update formula for alpha is very intuitive. Right? What is alpha actually? Alpha, what does it intuitively represent? It is the probability of y, right? That means in some sense, the estimate for this is what? The number of examples belonging to that cluster. Right? But what is y of x? It is some kind of a soft membership, right? It basically tells you what is the likelihood of a cluster ID given an example, right? So it's like saying you are asking each example xi, what is the likelihood that you belong to a cluster, particular cluster y, and simply adding up all those likelihoods and properly normalizing it. The denominator is nothing but the normalization constant, right? So instead of, see, in a supervised setting, what will you have? In a supervised setting, you will have hard values for this. Either, so you will have something like xi, yi. That means what? Probability with yi is 1 and every other y is 0. That's like hard clustering, right? That's what supervised learning data would look like. It would assign xi to a particular cluster yi. Now this is like soft, right? This is the only difference is it's soft. For each xi, I have a soft value of likelihood associated with every cluster ID. I am just taking for this particular cluster across all examples and properly normalizing. And what am I doing? So all of these calculations are based on the current value of the iterate. That means my current belief of the model. So using the current belief of the model and using the natural update, I am updating alphas, right? Similarly, there is an update formula for W's. So at the qth iterate, you will simply do the following. You will solve the following problem. So the qth iterate W, you will do the following. So the usual formula for MLE looks like this, right? I hope all of you remember. This is how it looks like, right? But there is a small change in this case. You will only take examples belonging to that cluster in the soft sense, that's all. So if you are building the yth component in the pth iteration, then you will basically weight these examples with the current, in the qth iterate, then you will take the current iterate belief value, and then with that for y given xi, right, and then sum over, normalize it properly, right? So this is sum over all I equal to 1 to m p theta q y given xi. Okay, and of course this formula looks very very similar to the formula we had in the usual case. In the usual case, it's like saying, again in the supervised case, if xi is labeled with yi, then all probability goes to the label yi, right? So I'll basically, it's like restricting this sum to all those i's such that yi is a particular, or j's such that yj is equal to yi. That's what will be this, right? So again it is like soft clustering, right? So instead of, so while classification gives hard labels, this is looking at soft labels with the current estimate of the parameter, right? And then using the average, weighted average as the formula. Okay, so you do these two updates and keep on repeating the e step and the m step iteratively. Okay, now so I know that I have not spent enough time on EM algorithm, and that was by purpose. It was just to tell you that solving this complicated problem has this easy updates. In fact, this is, EM algorithm is very very simple to code. It may look complicated because it's the first time for some of you are looking at these formulae, but if you go home and think about them and understand why they are intuitive, it's actually very easy to code them, right? And surprisingly, EM algorithm performs in most applications far better, gives you far better clusterings than when you solve these optimization problems with gradient descent or so on and so forth, right? So for cases where there are hidden variables, the default algorithm you always try is what is called as this EM algorithm, okay, which has these intuitive updates. So we'll go through over these updates perhaps once more in the next class, once things have synced in your mind. But for now, we'll call it a day. Okay. So if you have any short questions, you can ask. Otherwise, I have to leave. Yeah.
So I have one question.
Yeah.
So we are always saying, like, when we are saying p theta of x equal to sigma I equal to 1 to k. So we are already saying theta is a parameterization of like alpha 1 to alpha k and w1 to wk, right? That means the number of clusters k, do we fix it when we are?
Yeah, good question. So in mixture models, we are fixing it. Whereas in the other cases, the number of clusters was a consequence, right? Now here you are fixing it. Yeah, that's the difference.
Okay.
That's one downside of this, but you have to live with it. Of course, there are ways of handling it. There are generalizations of mixture models where you can relax this condition. But here, yes, you will require to specify k. But in the dialect example, it makes sense, right? It is like saying you already know how many dialects are. That's a very small information to know, right? How many dialects are there in Telugu, or into how many dialects you want to categorize Telugu? That's a better way of saying. That's a matter of design, right? I mean,
but in that case, that may, okay. I mean, I mean, I can say this is probabilistic modeling, but isn't it like a classification also, sir? Like
That's
for
the
example,
connection I have shown just before. This is the connection to classification. It is like classification with outputs hidden,
okay.
right? So the outputs Y's are hidden.
No, I mean to say when we are fixing the number of clusters,
Uh,
that becomes a classification problem only, right? If we are
no, but you don't. For each X, you are not told what is the cluster ID. There is no supervision. You are only given
okay,
X1,
okay,
X2,
okay.
X2, Xm. That's all.
Okay. So we are just asking it to divide them into
Yeah,
this many clusters.
yeah, correct. So you are just giving data and say figure out which point goes where and how they mix, what are the components, everything. Correct.
Oh, okay.
So in the MLE, so the model, all this component business, everything is encoded into parameters, alphas and W's. That's how the model takes care about Y, the hidden variable Y. And how are the parameters learned? Through MLE. MLE is simply doing maximum likelihood, right? So it's just figuring out the values of parameters which give a maximum likelihood of the training data, maximum likelihood for seeing the training data. That's as simple as that.
Yes, sir. Yeah.
The connection comes when alphas turn out to be close to P star Y, for which there is no guarantee. I'm not saying there's a guarantee, but the hope is that they'll turn out to be close. If they don't, then you will end up having a modeling error.
Okay. Thank you, sir.
Okay, so let me stop here. If you have any doubts, you can ask in the next class. But please go through clustering once more, especially the mixture model part. And if you have any questions, we will take it up in the next lecture. Thanks. Bye.
Bye, sir.